If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Also, after watching this video, you may want to refer to some of the playlists that we have created for people who are interested in in-depth knowledge. These are the videos in the right sequence, which will give you thorough knowledge of the subject. Please share it with all others who might benefit. Let's get started.
So let's start with tokenize. Whenever we work on a language, often there is a lot of importance given to specific words, and words have different forms, right? So a lot of times we'll be working on specific tokens, and we may want to do treatment specific to the word form. So we may want to break the sentence into words and then work on it. So in NLTK, the most famous library in Python for natural language processing, we have a module called tokenize, and we're calling a class called word tokenize. As the name goes, it's going to break the sentences into tokens. And we are also downloading the punctuations from the NLTK library. Just run this. And we are defining a simple function, which is called tokenize. What it does is it takes the text as the input and gives its tokenized form. We could have done it without this function also. So it basically is going to apply the word tokenize function on the specific text and returns the tokens is what we are saying. Let's take an example text, which is, can you check if tokenization is different from dot split? So this dot lower, dot upper, dot title, dot strip, all these methods that you saw are pretty much inbuilt in Python. Similarly, there is a dot split. And we are just seeing if dot split output on a string is different compared to tokenization. You can compare it yourself. So we are taking this text and we are passing it as an input to the function called tokenize, and then we are going to run it. Let me just define the function first and then run this line, and you can see the output. So this is the dot split output, and this is the tokenization output. Do you see a difference between these? If you see it carefully, you'd be able to see that tokenize is calling out the punctuations properly. It's separately calling out these parentheses that you can see here. These parentheses belonging to this dot split have been called out separately. This question mark at the end has been called out separately. So it's kind of able to identify some of the punctuations also, which dot split is not able to do because dot split is only focusing on breaking the string wherever it encounters these spaces. It has a parameter inside which is called separator. By default, that's set to space. So all dot split knows is that whenever we encounter a space, we have to break the string. That's what it has done. That's why you see this dot split together. But in case of tokenization, if you see, it has even broken those parentheses and question marks as separate entities. So now let's talk about these stop words. So what are stop words? Basically the kind of words that you use in any language to give a structure to your sentence, but they don't really have too much of a meaning. These could be articles like the, a, an. These could be pronouns. These could be prepositions. Now, we need to import the stop words collection from NLTK library. So from nltk.corpus, we are importing these stop words and we are downloading it here using nltk.download. Then we have to choose these stop words specific to the language. So we are saying stopwords.words English. This is a part of the syntax. You don't have to do much about it. This is a standard syntax to get these stop words and then get the specific stop words for a given language that you're working on. I'll show you what these stop words are like. So this is a collection of stop words. You can say this is more like a list, and it's a long exhaustive list. As you can see, it has about 170 plus entries in it. Now what we are doing is we are trying to eliminate these stop words from a specific text. What we have is hello world, welcome to text processing. In this part, we are performing stop words. Okay, so we want to see how we can eliminate these stop words, right? So first of all, it's a bit technical, but let me just tell you, whenever you have to perform a search, the more convenient data structure for that is a set, not a list. List is something that's going to go from the first element to the last element, whereas the set as a data structure is much more convenient. Its time complexity is much less compared to the list. So we are converting these stop words into a set form. If you see this in the code, you may be wondering why are we doing that? Because for this example, it might not matter. But when you're dealing with a large data set, it begins to matter how efficiently, how fast you're able to get the information that's desired. So we are converting the stopwords.words English that we got earlier into a set. We could have just taken this stopwords also here. That's one and the same thing. And then what we are saying is, how do we read this expression? Let's see. So we're creating something that's known as the filtered text. And to read this, you start reading it from the for. So for each word in text.split. So this is the text. You know what would happen when we do a dot split. Dot split is going to break that into kind of tokens wherever it encounters a space. If the lowercase word is not in stopwords, then we are bringing that word and joining it back. So join is the opposite of split. Join brings everything back together. Split kind of breaks it. Once again, let's read this together. For each word in text.split, if word.lower, why did we do word.lower? Because all these stop words, if you see, are in lowercase. So if you search for an uppercase U here, Y-O-U, that would be found in stop words because you have everything in lowercase here. So we are saying if the word in its lowercase form is not in stop word, this is literally like English, not in stop words. So if you do not have that word in stop words, then you're bringing that word back. So this is what you're returning. And then you're joining it back with what? With spaces. If you don't give spaces, it'll merge all these strings together. Then we're printing the original text and the filtered text. Let me just run this for you. Okay, so hello world, welcome to text preprocessing. In this part, we are performing stop words. If you see what's the change here, hello world, everything is there, welcome, and this to has gone. Okay, and then in this has gone. Only the part piece is left. We are has gone, performing stop words. So stop words, generally, these words like are, is, the, and would not make sense in any analysis. And that's where we want to kind of eliminate them. That's where this is how this syntax helps us eliminate these stop words. So when it comes to stemming, we have multiple choices here. As you've seen in the theory videos, stemming refers to bringing the word to its root form, and there are multiple options available. Porter's stemmer is one of the classic stemmers introduced in 1980s. Then we had the Lancaster stemmer, which is somewhat rigid, as they say, somewhat ruthless. And then there is Snowball stemmer, which extends to multiple language. So we'll see how we can actually bring the words to their root form. One important thing to keep in mind for stemmer, as we emphasized earlier as well, is that these work on heuristics, which means they follow certain flat rules. They may convert a word to a state where it's not even in its canonical form. It's not a word that's represented in a dictionary. So all these stemmers could lead to certain changes in the words, which are not necessarily the dictionary forms, but it is essentially done to negate multiple variants of the same word when we are trying to analyze a language. That's the whole purpose. So let's start with Porter's stemmer. We're giving a list of words here, and we are calling the Porter's stemmer. Then we are saying for each word in words, this words is a word list, we want to apply Porter's stemmer. Note, stemming would be done at a word level. That uppercase, lowercase conversion and all you could have done at the string level also, but stemming is always done at the word unit level. So we are running a loop over this list and we are saying we want to convert it to a word. Now, why are we not using a set here? Because in this case, right now, we definitely want to go over this entire list. We don't want to choose a specific entry and work on it. That's why we are leaving it as a list right now. Let's just apply the Porter's stemmer and look at the output. What does it look like when we apply Porter's stemmer? So running has been reduced to run, jumps has been reduced to jump, swimming has been reduced to swim, happiness. So this is where I said it could be a non-dictionary form. For example, happiness is a word that we understand. What is H-A-P-P-I, happy? So that's a little weird. Quickly, this Y has been converted to an I. So this is based on certain rules that it follows. Talked has been converted to talk. Walking has been converted to walk. So most of the cases, the verb forms like ing and s and the past tense, etc. have been corrected. But for some words, it's kind of taking a rule-based change. Any ness, for example, has been replaced with an I. Y has been replaced with an I. So there could be certain differences in the way it deals with different words. Now let's use the Lancaster stemmer. So this is just for illustration purposes. You don't have to necessarily apply multiple stemmers together. Porter's stemmer, being the earliest and being the simplest, is still one of the fastest. Lancaster stemmer, as they say, goes a little ruthless. It means it may just abruptly end a few words here and there. And Snowball stemmer has a strength that it works with multiple languages. So you can choose to work with one of these. So let's see if we take the same input for Lancaster stemmer, the syntax is one and the same. So for each word in words, we are applying the Lancaster.stem. It was introduced by the Lancaster University. That's why. Okay. So if you see, the output is slightly different. For the words like running, jumps, swimming, it's one and the same in Porter's stemmer and the Lancaster stemmer. But happiness, if you see, it has reduced to a form called happy. Quickly has been reduced to quick. In case of Porter's stemmer, that was reduced to quickly with an I. And talk and walk are against that. So they have some overlaps and some differences. Now let's call the Snowball stemmer exactly the same kind of syntax. You just instantiating a Snowball stemmer. Because it works with multiple languages, the difference is that we're giving the language input also, that we're dealing with English. Rest is one and the same. For each word in words, we are applying the Snowball.stem. And let's see what's the output like. So if you see, this again has reduced the happy to an I, like the Porter's stemmer. Quickly, there's a difference. If you see, quickly in case of Porter stemmer was reduced to quickly with an I. In case of Lancaster stemmer, it was quick, and Snowball is also saying quick. However, between Lancaster stemmer and Snowball stemmer, if you see, there's a difference in the way it deals with happy. With happy, it deals pretty much like the Porter stemmer here. So again, there are overlaps and differences at times. Choose one of these as you would want to work on it. So let's talk about lemmatization. The fundamental difference between lemmatization and stemming is that lemmatization is going to do a lookup, and it's always going to return the outcome, which is a dictionary form. Whereas the stemmers don't really care for the dictionary form of the word. So lemmatization is not just a rule-based thing. It's based on the lexicon. It's based on the understanding of the language and vocabulary. So this is a little more elaborate approach, you can say, and that's what, of course, makes it somewhat slower. But it's not bad. If you want to have the end outcome that you want the users to be able to comprehend, then maybe lemmatization would be a better choice for you. Let's just call the NLTK library. We're downloading the WordNet because this is where it's going to do the lookup from. And then from the NLTK.stem, from the same module, we are calling the WordNet lemmatizer here. So we are instantiating WordNet lemmatizer, same kind of input we're giving, and we are saying for each word in words, let's apply the lemmatize. Last time we were doing stem only. Let's see. So if you see, running remained running, jumps became jumps, swimming remained swimming, happiness is pretty much intact the way it was. It did not change it to happy, quickly remained quickly, talked and walking. These pretty much remained the same in this case. Because this is not a proper sentence, these are some words. So for most of these words, it didn't find a need because we didn't really give a sentence, a proper language input. We gave some units of words and it didn't really change it. However, as we go forward and practice on some text, some examples and case studies, you will see there would be a clear difference between the lemmatizer and the stemmers. Because lemmatizer would make its choice whether it wants to cut a word or not based on how it is being used, where it is being used.